Hello everyone, my name is Kaushik Vemla and I will be starting for the team presentation of Team Benjamin. Our topic is geometric transformations. We will be covering these topics individually. Our team will be covering these topics. I will be covering 2D transformations, explaining the concepts, translation, rotation, scaling, and homogeneous coordinates. Srija will be explaining inverse transformation, composite 2D transformation. Pujita will be explaining computational efficiency, rigid motions, and reflections. Sai Krishna will be explaining shear in 2D and raster methods. Sai Nikhil will be explaining transformation between coordinate system, 3D rotation. Sai Chaitanya will be explaining 3D scaling, reflection, and transformation design, and also design examples. To start things off, what is transformation? Transformation means changing some graphics into something else. It might be changing an image to make it look better, make it look sharper. It might be it might be architectural design to make the house, which should be a 30 inch by 15 inch or 10 inch, to make it look like a small paper in our hand. Anything can be considered as transformation. Some of the types of transformations are translation, rotation, scaling, reflection, and shearing. If the transformation which we are speaking takes place on a 2D plane, it is called 2D transformation. Transformations play an important role in computer graphics to reposition the graphics on the screen and change their size or orientation. As we can see in this image 1 to image 2, we have a rotation happening. Image 2 to image 3, we have a we, we have a translation happening. Translation, straight line movement of an object from one position to another is called translation. To translate a point from coordinate position x comma y to another x1 comma y1, we add algebraically the translation distances tx and ty to original coordinate x1 equal to x plus tx, y1 equal to y plus ty. As we can see in this image, we have seeing a translation of the triangle PQR to P dash Q dash R dash, given the translation distances as x equal to 7, tx equal to 7, and ty equal to -4. Matrix notation for translation. Matrix notation is representing the operation which has been performed in matrix notation in matrices. It is simpler and is much more useful in advanced level and many other concepts which we will be explaining in the later concepts. Matrix form of the equations x dash equal to x plus tx and y dash equal to y plus ty can be written as p dash equal to p plus d, where p dash equal to x dash y dash, p equal to xy, t equal to tx ty. The next topic we'll be covering is rotation. Rotation is a process of changing the angle of object. Rotation can be clockwise or anti-clockwise. For rotation, we have to specify the angle of rotation and rotation point. As seen in the image below, we are showing rotation of a point in anti-clockwise direction and clockwise direction. As you can see, this is anti-clockwise and this is clockwise. Rotation can be done in two ways: rotation of an object around origin and at an arbitrary point. I'll be starting with object around origin. As we can see in the image, we are rotating the image O with an in anti-clockwise direction for theta degrees, and we assume we got the new point as O dash. Let us consider it as x new as x dash y dash and x old as x comma y. Using standard trigonometric calculations from the image, we say that it creates we create it creates some triangles. Using standard trigonometric calculation, we can derive that x dash equal to x cos theta minus y sin theta, y dash equal to x sin theta plus y cos theta. Matrix notation for rotation. We can write these two equations in matrix notation as x dash y dash equal to xy into cos theta sin theta minus sin theta cos theta. This can also be written as p dash equal to p matrix multiplication, or rotation at arbitrary point. Rotation at arbitrary point involves three steps. We basically translate the arbitrary point towards the origin. We rotate we perform rotation operation, and we translate back the origin to from origin to center of rotation. As we can see in this image, we have translation of the center xpyp from xpyp to center. And, this can be seen in B, explaining it as step 1, and then we'll be performing rotation operation, which is being performed in step 2 in figure C, and in figure D we can see that it's being translated back from origin to xpyp. Scaling is another operation which can be performed using transformation. This scaling is used to alter or change the size of objects. The change is done using scalar factors. There are two scaling factors, that is Sx in x direction, Sy in y direction. If Sx equal to Sy, it is called uniform scaling, else it is called non-uniform scaling. Matrix notation: x dash y dash equal to xy into Sx0 Sy. P dash equal to P matrix multiplication of S. We have an image showing uniform scaling and non-uniform scaling. Uniform scaling, as we can see, the square increased in the same manner. All the sides are equivalent. It has retained its properties of a square. Whereas we can see the image that that the width has been enlarged a lot, but the height has been enlarged a very little. And we can see that it became way more of a wider rectangle. We changed the objects we have changed the properties of the object to a certain range. Homogeneous coordinates. Consider this previous scenario of rotation at an arbitrary point. It is taking us 3 steps. To solve these kinds of scenarios, we will be using homogeneous coordinates. Homogeneous coordinates for a two-dimensional coordinate position x, y is represented by triple coordinates x, y, and w. In homogeneous coordinates, you represent points in a 2D space using 3 real numbers. If it's a 3D space, we'll be using 4 real numbers. If for the 2D space, x, y will be representing it with x, y, w, where x by w, y by w represent the corresponding point in Euclidean coordinates. Here, w is a scaling factor or weight. To convert back to Euclidean coordinates, you simply divide x and y by w. As shown in the image, we get we are showing the weight w equal to 3, and we are getting point as 21 and 15. If we have w equal to 1, we get the point as 7,5. For the Euclidean coordinate 7,5, we can see that there are multiple homogeneous points. In actually, we can get infinite number of points for a single given Euclidean coordinates. This is one of the feature of homogeneous coordinates. These are the matrix notations for the translation, scaling, rotation in anti-clockwise and rotation in clockwise respectively. As we can see, tx, ty, sx, sy, cos theta, theta. And in the matrix representation is p dash equal p plus t, p dash equal to p into s, p dash equal to p into a, where p is x, y, 1, t is translation, s is scaling, a is the rotation matrix.
Now I'm going to continue about the inverse transformations. As I have mentioned about the translation, rotation, and scaling, now we are discussing about the inverse of that. And generally, when we consider a matrix as 1, 0, t of x, when t of x and t of y are the translations, in inverse, we consider it as minus. So, and as on translation, it's just like a shifting of the point. In this context, generally, while dealing with planes, we refer with respect to origin. So translation is mostly used while considering a point changing by its angle or any other scaling things. In rotations, we the overall multiplication matrix would be of cos theta sin theta o minus sin theta cos theta o 1. uh, in this process, we are going to rotate the plane by certain angle in positive or negative axis depending upon our requirement and the plane's axis. And scaling, it's like diminishing or enlarging an object by a particular factor. A value something less than one is considered something more than one is considered to be enlarging, and something less than one is considered to be diminishing, until and unless a small change doesn't affect the plane as a whole. uh, then is it possible to do multiple transformations at a time? Yes, the answer is yes. In transformations, when we perform multiple operations, it must be always in a sequential order. And this process of doing multiple transformations at a time is known as a composition or a concatenation of the transformations. And uh, in this process, generally the order of the process matters much. For example, we are first performing scaling and then rotation. That the final output will not be same as like for example, let me take m1 and m2 are the two operations that we are performing, and the final new plane would be p dash. uh, the operation m1 m2 into p is not at all equal to m2 m1 into p. So for a two-dimensional for a two-dimensional plane, for translation, the equation would be in this form. The final coordinates for the translated plane would be, with respect to x coordinates, it will be t1 plus t2, where t1 and t2 are the two different transformations that we have made for a particular plane. And for y-axis, it would be t1 plus t2 with respect to the two operations that we have did. In the same way, while coming to the angles, theta 1 and theta 2 are the two angles that we have rotated the plane to. Then the final overall affected plane would be suffering from the both theta 1 and theta 2 references. And while coming to scaling, as diminishing or enlarging multiplies as we are increasing. So with respect to x-axis, it would be S1 and S2, where S1 and S2 are the scaling factors that we have used, and similarly for the y-axis. Here we can observe an example. As I have previously mentioned, while we are performing any operation on a plane, it's like we need to take the object with reference to the origin and then perform our scaling or any other translation. Here, the image represents this is the original image. Then we have translated the object with respect to origin, and then we have scaled that particular object. Here we can see the image has been enlarged, and then we have rotated it by 90 degrees. In this form, the final output would be in this format. And again, we need to convert, like we need to make this image shift to the original position using the translation again. So the overall matrices we will be of this form. First, we can see first we have performed translation here. So for translation, the matrix would be in this form. Then scaling. This is a matrix for the scaling after translation. Sorry. This is rotation. The final matrix for the rotation, when we are rotating, where we have rotated the image in a counterclockwise direction, the final resultant matrix will be of this form. So, as I've mentioned, when we are doing multiple translations, the overall effect would be the product of all the transformations we have made. And for an instance, let us consider this as M1 transformation, M2, and M3 transformation. So, M1 into M2 into M3 is not at all equal to M1 into M3 into M2. So, next, coming to rotation of rotation with respect to an arbitrary rotation on an arbitrary plane. First, this is the original position of the object. The sequence of steps would be: first, we need to take the original position of the object, then make it centered with the origin, and then rotate it or scale it or any other transformation with respect to the origin, and then translate the object to its original position. So here we can observe in first image, the object is in the positive coordinate. Then it has been transferred with respect to the origin. And then the rotation, here we can observe the difference in the angle, the base of the triangle. So it is being rotated with some angle. Here it is 90 degrees when we see the both images. And then we are shifting the image to its original position. So as in the original position, this is the new position and the new rotated angle for the object. So mathematically, we can represent this as in this form. So first, the translation was with respect was shifted. The plane was shifted to the origin. So this would be the matrix where x and y are the points we have shifted to. And then this is the matrix for the rotation of the image. And then the translation back to the original position would be this. So the overall final matrix can be represented as of this form, where first we have translated, rotated, and then translated the whole plane. And the resultant matrix would be of this form, where the first row has the effect of first translation, then rotation would affect with all the thetas, and then the second re-referenced planes would be with xr and yr here. Then now coming to scaling with respect to the arbitrary point. So here also, as the previous rotation, the original position, this is the original position of the object. Then we have we need to move it to the origin or the translation towards the origin, and then we have enlarged or scaled the object. Here we have enlarged it, or we can generally diminish also. Then the object is moved to its original position or the to original position, and this shows the final overall affected plane. Again, coming to the mathematical representation, this would be the mathematical representation for that, where first one is the translation for the origin. This is for enlarging with a factor of s of x and s of y on the particular coordinates, and then making the object back to its original or arbitrary positions. And this would be the final matrix, where first one is the translation, then scaling, again the translation in opposite direction. Now Pujita will continue the presentation.
Good evening. I'm Pujita from Team Benjamin. The topics I'm going to present are scaling of an object in specified perpendicular direction. Is order of these transformations relevant? And the computational efficiency of using homogeneous coordinates. And what are rigid motions and rotation using orthogonal vectors? And also we are going to see about reflections transformation and reflections with respect to x and y axis and with respect to diagonals. So coming to scaling of an object in a specified perpendicular direction, it involves changing the size of an object along an axis that is perpendicular to a given direction. So the process of this includes rotate the object so that the directions for S1 and S2 coincide with x and y axis respectively, and scaling of an object with respect to the origin using S1 and S2, and later we need to rotate back the object to its original orientation. Coming to the composite matrix resulting from the product of these three transformations is R inverse of theta multiplied by S of S1, S2 multiplied by R of theta, which results in this matrix. And coming to the example, here we are going to transform square into a parallelogram by stretching the diagonal. And the process includes these three steps, which are rotating the square until the diagonal align with y-axis and scaling the square by using S1 equals to 1, which is scaling metric 1 is equals to 1, and scaling metric 2 is equals to 2. And rotating back the square to its original position, which in turn gives the parallelogram to us. And coming to the order of transformations is relevant or not. So here we can see multiplication of matrices obeys associate law. For example, if there are three matrices such as M1, M2, M3, then product of M3, M2, M1 is equals to product of M3, M2 and M1, which is equals to product of M3 and M2 and M1. So in a composite transformation, the order of individual transformations is important. For example, if you first rotate, then scale, then translate an object, you get a different result than if you first translate, then rotate, and then scale. For composite matrix, depending on the order of the transformations, we can multiply either from left to right or right to left. And coming to matrix multiplications, we know that matrix multiplications are not cumulative, which means that product of M2, M1 is not equals to product of M1 and M2. But in some special cases, transformations are cumulative. Coming to some of the specific cases are the sequence of transformations that are of same kind, like two successive translations, two successive rotations, and two successive scalings. The final position will be the same. So coming to the second case, rotation and uniform scaling are also cumulative, which says that we can first rotate the object and then scale the object, or first we can perform the uniform scaling and then rotate the object. In the both cases, the final position will be the same. And in third case, translation and rotation of an object are also cumulative. As shown here, The original position of the object is as shown in the first image, and if we first translate the object and then rotate the object, or if we first rotate the object and then translate the object, final position of these two cases will be the same. So coming to the computational efficiency of using homogeneous coordinates. Here we can see the representation of a two-dimensional coordinate position x, y in a three-element representation xh, yh, h is called homogeneous coordinate. So two-dimensional transformation with any combination of translation, rotation, and scaling can be represented as shown in here. This is the matrix representation of two-dimensional transformation with any combination of these three transformations. So as we know, homogeneous coordinates simplify the representation of transformations using matrices. We can represent translation, rotation, scaling, and shearing operations in a consistent manner. So when we multiply a point represented in homogeneous coordinates by such a matrix, the computations can be more efficient due to the regular structure of the matrix. And homogeneous coordinates simplify the concatenation of multiple transformations. This is more efficient than applying each transformation separately. Here the four elements R, S, J, K are the multiplicative rotation scaling transformations, and the elements TRSX and TRSY are the combination translation distance, rotation angles, and scaling parameters. So here we can see if the object is to be scaled, rotated, and translated, then the values for the composite matrix are described as T of Tx, Ty multiplied by R of Xc, Yc, angle theta multiplied by S of Xc, Yc, Sx, Sy. So the individual transformations has to be done each transformation at a time and require more steps. Whereas in homogeneous coordinates, the homogeneous coordinates simplify the concatenation of multiple transformations, and in summary, they simplify many mathematical operations and make it easier to perform transformations. So for small angles, which are less than 10 degrees, the cos theta is approximately equal to 1 and sin theta value is very close to theta in radians. So composite transformations often involve inverse matrices, which can be generated with simple procedures like for a translation matrix, we can find inverse matrix by changing the sign of the translation distance. And for rotational transformations, we can find inverse matrix by matrix transpose or by changing the sign of the sign terms. So what are rigid motions? Rigid motions change the position or orientation of the object without changing size or shape. Translation and rotation transformations to the object are examples of rigid motion. The general form of two-dimensional rigid body transformation matrix is as shown here. Here, the RJK terms are the multiplicative rotation terms, which are RXX, RXY, RYX, RYY. And TRX and TRY are translational terms. Sometimes this rigid body transformation in a coordinate system is referred as rigid motion transformation. The important property of this matrix is that upper left 2 by 2 matrix is an orthogonal matrix, which is Rxx, Rxy, Ryx, Ryy. If we consider elements in each row as a vector, that is Rxx, Rxy as one vector and Ryx, Ryy is another vector, then they form an orthogonal vector set. That is, each vector has unit length and vectors are perpendicular, which results in dot product is equals to 0. When these unit vectors are transformed by rotation submatrix, then the vector Rxx, Rxy is converted to unit vector along x-axis, and the vector Ryx, Ryy is converted to unit vector along y-axis of the coordinate system. And if the rigid body transformation is done by first rotating the object at an angle theta about a pivot point xr, yr, and then translating the object will be represented as shown here. And now coming to reflection. A reflection can be thought as of folding or flipping an object over the line of reflection. And the original object is called the pre-image, and the reflected image is usually called as image. And the image is usually labeled as A, B, C. And an object and its reflection have the same shape and size, but the figures face in opposite directions. Relative to an axis of reflection, the object gets rotated by 180 degrees around the axis of reflection as shown in the figure here. And the axis can be in or perpendicular to xy plane. Coming to the reflections with respect to x-axis. This transformation involves flipping an object over the x-axis, and the x-coordinate of each point remains the same while the sign of the y-coordinate changes. Here we can see coordinates of point C 4, 2 are changed to 4, minus 2, where we can see the x-coordinate of the point remains the same while the y-coordinate sign changes. Coming to reflections with respect to y-axis, this transformation involves flipping an object over the y-axis, and the y-coordinate remains the same while the sign of the x-coordinate changes, as shown in the figure here. And coming to reflections with respect to diagonals, in this we have two cases where reflection with respect to the diagonal y equals to x and reflection with respect to the diagonal y equals to minus x. In the first case, we can see here this transformation involves flipping an object over the line y equals to x, and points with coordinates a, b will swap places with points b, a as shown in the figure. And coming to the second case, which is reflection with respect to the diagonal y equals to minus x. This transformation involves flipping an object over the line y equals to minus x, where the points with coordinates a, b will swap places with points minus b, minus a as shown in the figure. So to simplify these different types of reflections, we can follow these simple rules as shown here. Thank you.
Hi, this is Sai Krishna, and today I'm going to continue with the previous whatever way my teammates has been done with their topics. So coming to my topic, the reflections with respect to an attribute axis. After the diagonal axis, now I'm continuing with the attribute axis, which is an reflection axis will be a y is equal to mx plus c. Here you can see the steps for the following steps. Translating the line from the origin, like from the attribute line to origin, it's gonna be translated to here, and then it's gonna be rotated to the origin to the minus theta, so it's gonna be rotated towards this. And the reflection matrix, it's going to be reflect the matrix of what we have been in our original position. So after that, the rotation going to be taken into the reverse to the minus theta, as we've seen in the following image here. Translate the line back into the arbitrary, which is an original position to the previous original position. So by final matrix will be a t is equal to translate into reflection into reverse reflection into a translate line back to the orbitary. And now which is shear. The shear is a transformation that slants the shape of the object is called as shear transformations. A transformation in which all points along given a line L remains fixed while other points are shifted parallelly to the L by distance proportional the perpendicular distance from L.
You're gonna see these pictures on the next slide. The shearing plan figures does not change its area but changes its only shape. The shear can also generalized in the three dimension in which planes are translated instead of lines. There are two shears transformation. One is x shear and y shear. One shifts x coordinate value, another shift y coordinate values. However, in both cases, only one coordinate changes its coordinates, another preserves its value. Shearing is also termed as a squeak. And and distorts the shape of the object, commonly used to shift x and y values. In any real world can be used as a negative number shift to the left. Coordinate positions are shifted proportionally to the perpendicular distance from the reference line. So here you can see the images over there, which has been shifted to the perpendicularly towards the x value side. You can see the equation x1 is equal to x plus shear xy. You can see here the matrix of shear x, which is gonna be like 3 by 3 into matrix, and this is the values for the y coordinate of y axis. So the shear how it's going to be performed here. So you can see the matrix of the y axis coordinates and can be expressed as a sequence of basic transformation scales along the diagonal with the shear maintain the length and orientation parallel to the references here in the image. Shifts are equivalently to translations. And raster methods. Alternative methods for performing 2D transformations stores information as a color pattern in the form buffer. Functions that work on a pixel area for the raster operation. Moving a block is called as a block transfer, like is also called as a pixel it and a bit it. And it doesn't need any arithmetic operation to perform this. Here you can see the image here which has been shifted from here to object to the transformation. Then coming to next slide, the raster methods, then it gonna be take 90 degrees rotation, simply rearrange the elements in the pixel array, reversing the pixel value in each row, then swapping the column and rows rotation 90 counterclockwise. Okay, here you can see that the matrix with 4 into 3, if it is rotated into 90 degrees to comes into 3 into 4, and it's again rotation into 180 degrees, so it comes in the rows and columns has been arranged in 180 degrees as the matrix is 4 into 3. And coming to next slide, the rest rotation that's orange multiplies 90 degrees need extra processing. Destination pixels are mapped onto the rotation area. Calculate the amount of overlap and average the color of the overlap sources pixel. The weighted by percentage of area overlap could use an anti-aliasing, and the scaling is also done similarly. The reflection reverse rows and column value and combined translations. Shear shift area value position also rows and the columns. The next topic is 3D shearing. The transformation will modify the shapes of the object. This also useful the perspective projection. Here you can see the image. You can see the image in two different ways, like in the two different perspectives. When an object viewed from the different direction and the different distance, the appearance of the object will be a different. Such view is called as perspective view. The matrix of the representing of 3D shearing in the perspective view is here. The matrix of shear 3D is equals to is the matrix 4 into 4 is the really based on the shear. And next topic gonna continue as my friends gonna continue in my team. Thank you.
Yeah, good afternoon, everyone. Today I'm going to present about transformation between coordinate systems, and later on I'm going to talk about 3D transformations. So coming to transformation between coordinate systems, generally computer graphic applications involve various coordinate systems. Transforming coordinates between different coordinate systems, such as converting world coordinates to pixel coordinates. Modifying the camera or viewer's position and orientation to change the perspective or view of a 3D scene. So a transformation between coordinate systems are very essential for computer graphic applications. In computer graphics, coordinate system transformations are the backbone of creating visually appealing and interactive digital experiences. These transformations empower us to position and animate objects, seamlessly switch between different perspectives, and manage complex scenes. Whether it's aligning elements on a screen, animating objects smoothly, or adapting to various display sizes, transformations are the fundamental tools that bring order and versatility to the world of digital design. So let's consider an example of transforming a point in a 2D space. So to transfer the point in a 2D space, first we need to translate the origin of xy to xy and then rotating x dash to x to align with the x-axis. As we can see in the picture over here, first we need to do a translation, then rotation along the x-axis, and the final result will be the r cross t, which will give us the correct point after transforming the coordinate system. Coming to 3D transformation, 3D transformation is the process of manipulating the view of a 3D object with respect to its original position by modifying its physical attributes through various methods of transformations like translation, scaling, rotation, and shear. 3D transformations play a crucial role in presenting and visualizing three-dimensional objects and scenes on a 2D space or other output devices like a gaming console or TV screen. So these transformations are fundamental for creating realistic and visually appealing 3D graphics. These transformations are often combined to achieve complex effects, and they play a crucial role in creating 3D graphics, animations, and simulations. So one of the 3D translation. So 3D translation is similar to 2D translation with extra coordinate, as it involves moving an object or a point in a three-dimensional space along one of the x, y, or z axis. This transformation is typically used to change the position of an object within a 3D scene. So it's nothing but the process of changing the relative location of a 3D object with respect to the original position by changing its coordinates. So as we can see in the picture over here, so after translating a point to the new position, to x dash, y dash, z dash, we can see the resultant matrix with tx, ty, tz, which are the translation distances for x, y, and z axis. And in mathematical notation, we can represent the new point as p cross p, where p is equal to x, y, z, and p dash equal to x dash, y dash, z dash, which is the new position of the object. Yeah. Now let's talk about 3D rotation. So in 3D rotation, it involves changing the orientation or angular position of an object or a point in 3D space. Rotations are used to manipulate objects, view them from different angles, and create complex 3D animations. So there are three kinds of rotations where we can rotate an object just parallel to a specific axis, so that coordinate about which this object rotates remains unchanged, and the rest of the coordinates get changes. In total there are three kinds of rotations that are possible: rotation about the x-axis, rotation about the y-axis, and the rotation about the z-axis. Let's have a look at the rotation about x-axis. As you can see in the picture here, we are rotating an object around the x-axis. So we can, in mathematical perspective, we can extend the 2D rotation equations to 3D. As you can see below, x dash remains x as we are rotating an object around x-axis, and y dash equals to y cos theta minus z sin theta, and z dash equals to y sin theta plus z cos theta. In mathematical notation, matrix notation, we can represent it as the mu position of object as the matrix as given here. Similarly, rotation about y-axis, we can see in the picture the object is rotated around y-axis, and similarly we can use the same 2D equations where x dash equals to z sin theta plus x cos theta, and y dash equal to y, and z dash equals to z cos theta minus x sin theta. In matrix representation, it can be represented as given in the picture here. Yeah, finally, the 3D rotation around z-axis. As we can see in the picture over here, we have rotated an object around z-axis. So similarly, we can extend the 2D rotation equations to 3D as well. So the x dash equals to x cos theta minus y sin theta, y dash equals to x sin theta plus y cos theta, and z dash equal to z. In matrix representation, it can be represented as in the picture here. And also, we can rotate an object around an arbitrary axis. So when the object is rotated about an axis that is not parallel to any one of the coordinate axes, then additional transformations are required. First, we need to align the object, and then the object is being back to its original position. We need to follow the few steps here. So to rotate an object around an arbitrary axis, first translate the object to the origin. As we can see in the first picture here, we need to translate this object to the origin in the step 1. In the next step, we need to rotate the object so that axis of object coincide with any one of the coordinate axes. After moving it to the origin, we need to make sure that it aligns with one of the coordinate axes, which can be either of x, y, or z. In the next step, we need to perform a rotation about coordinate axis with whom the coinciding is done. So now in the next step, we need to rotate an object around one of the axes where the object is parallel to the one of the axes. After rotation around the axis, we need to apply the inverse rotation to bring rotation back to the original position. And the next step, we need to bring the after we need to apply the inverse rotation to bring the object to its original position. Then the final step, translate the rotation axis to its original position. There is also other way of rotating a 3D object using quaternions. Okay, the technique 3D rotation using quaternions is a powerful technique for performing smooth and efficient rotations in 3D space. Quaternions are a mathematical construct that avoid some of the complexities associated with other rotation representations. They provide a mathematically robust way to present and manipulate rotations, making them a popular choice in game development, 3D modeling, and other 3D applications. A quaternion represents two things. It has x, y, z components, which represents the axis about which the rotation will occur, and a term w, which represents the amount of rotation that occur about the axis. As we can see in the equation here, the quaternion is defined as q equals to w plus xi plus yj plus zk, where w, x, y, z, x, y, and z are real numbers, whereas I, j, k are imaginary numbers. Yeah. Coming to the, let's consider these two quaternions Q1 and Q2. which are defined as W1, X1, Y1, Z1, and W2, X2, Y2, Z2. So Q1 cross Q2 cross W will be the W1, W2 minus X1, X2 minus Y1, Y2 minus Z1, Z2. The important thing here to note down is that when Q1 cross Q2 is not equal to Q2 cross Q1, as quaternion multiplication is not cumulative. So in mathematical notation, we can represent a quaternion X, Y, Z, W as M equals to as a matrix given here.
Hello everyone. So today we are going to continue our presentation from my friend. So today in this presentation we'll be covering 3D scaling on an arbitrary point, 3D reflection, 3D shearing, transformation between 3D coordinate systems, and at last we're going to look at some 3D transformation examples. So let's begin. So first, we have matrix 3D scaling. So what does 3D scaling mean? So 3D scaling means nothing but whatever we have seen in the 2D scaling, but over here we are doing the same scaling in the three-dimensional space where we have a new z-axis. So which means in simple terms, we are expanding matrix representation expands from 2D scaling to accommodate scaling in the 3 dimension. That's a simple explanation and seamless extension of these concepts and principles applied in 2D scaling to 3D scaling space. It is crucial for resizing and adjusting objects within a 3D environment accurately. That's very important because if that hasn't been done, then entire object shape will be changed. And next, so let us over here. I've represented matrix S. So it stands for scaling matrix that determines the scaling factors along x-axis, y-axis, and z-axis. Over here we can see which are defined by sx, sy, and sz. So and p dash represents the transformed point after the scaling in the 3D space. And P signifies the original point, P's position in 3D space, and the equation demonstrates the P's point's position changes after applying the 3D scaling transformation using the scaling matrix. So over here, we'll be using this matrix and we are going to multiply with x-axis, y-axis, and z coordinates based upon the scaling factor. Then it is like P equals S into P, S dot P. So over here, as we can see, as you can see, there's a pyramid type of object where which is placed in XY coordinate space. So what you need to do is we need to take the P is the point where the original object is placed. Then we're gonna move that object to the origin. Then we'll be scaling based on the scaling factor. Again, we're gonna replace the object to the original point, which is P. That's how scaling would be performed. So certain graphic software may offer scaling capabilities exclusively concerning the coordinate origin. In such scenarios, the procedure involves the subsequent steps. So know the given point of the coordinate origin, implement the scaling transformation in relation to the coordinate origin using the designated scaling equation. And at last, return the point to its original position by applying the appropriate translation. So this would be the first, then we're gonna bring the object to the origin, then scale according to scaling factor, and bring the object to its original position. Yeah. Now comes to the 3D reflection. So 3D reflection in computer graphics is used to reflective objects like mirrors and shiny surfaces. Reflections may be and x-axis, y-axis, z-axis, and also in xy plane, yz plane, and even zx plane. The reflection relative to a given axis are equivalent to 180-degree rotations. So this is a sample example of 2D reflection. So over here we can see when there is an object on in this coordinate space, the reflection. So in this coordinate space, the reflected image would be have to present 180 degrees inwards to it. Same to XY plane and Y-axis and even XY plane. Over here, this is a good example for 3D reflection. We have an object in ZX plane. So since it is in ZX plane, it has to reflect on inverse to its 180 degrees, which would be ZY plane. Over here, yeah, based upon the reflection side, we need to reflect. So yeah, this is the reflection is performed. And 3D sharing, sorry, oops. 3D sharing transformation. So basically 3D sharing involves modifying the shape and geometry of objects in 3D space, particularly variable for achieving realistic perspectives projections. What is perspective view? So perspective view refers to varying appearance of an object as observed from different directions and distances, and utilizing 3D sharing transformations to accurately represent how the object would appear in real world perspective view. So over here we have an example to draw a cube. To draw a cube 3D on a screen 2D, alter the values of x and y not are proportional to the distance from z reference. So this is how, yeah, there's a sample example. And in 3D sharing, suppose if you have to perform 3D sharing in YZ with respect to X, so this is the matrix that we need to consider. And in ZX with respect to Y value, then sharing XZ, then this would be the matrix. This is how the matrix is represented. Same goes with XY with respect to Z, and sharing along the z-axis since we are sharing in the three-dimensional space. So sh of shx comma shy multiplied by p is equals to p dash. So over here p is the original point of the object. These are the original points, and these are the shared matrix points. This is how once we multiply, we're gonna get the final destination point where we need to present object. When transitioning between coordinate system, it is assumed that it is assumed that just a moment, yeah, when transitioning between coordinate system, it assumed that a new x dash y dash z dash system is defined in relation to an existing xyz system. To map xyz coordinate descriptions to the x dash y dash z dash system, we begin with translation that aligns the x dash y dash z dash coordinate origin with xyz origin. Subsequently, a series of rotations are applied to align corresponding coordinate axes. If there are differences in coordinate intervals due to scaled variation in the two systems, a scaling transformation may also be required for compensation. The rotation for coordinate axis transformation can be constructed using unit axis vectors, transforming unit vectors u dash, v dash, and w dash on xyz axes respectively. Coordinate system transformation assumption is an assumption that x dash y dash z dash system defined relative to the xyz system. Coordinate mapping means transfer XYZ coordinates description to X dash, Y dash, and Z dash system. Initiate with the translation, align the coordinate origins X, Y, Z to X dash, Y dash, Z dash. Alignment of axes, a sequence of rotations, align corresponding coordinate axes. Facilitates seamless translation between coordinate systems. Handling scale variation. If different scales are present in the coordinate systems, applying scaling transformation to compensate for interval differences. Rotation matrix for axis alignment. Utilize the unit axis vectors to construct the rotation matrix. Achieves transformation of unit vectors U dash, V dash, and W dash on the X, Y, Z axes respectively. So let us look at some 3D transformation examples. So over here, this is a 3D translation example of a translation, how we are translating three-dimensional object. And same goes with the rotation with respect to the origin. Over here, same with respect to an arbitrary point, rotation with respect to an arbitrary point. Yeah, again, one more scaling. So first we have an object, then this is the P, then we're gonna bring that point to the origin, then we're gonna scale, then we're gonna replace P with the original point, So these are the reflections, and this is the sharing with respect to the x-axis. So this is a translation of the chip object by 3, 2, -3. And same the rotation. Over here we have rotated 60 degrees. And scaling by factor of half and 3, as you can see over here. And reflection. So this is how the scaling is performed, as we have already discussed. These are in software examples, translation. This translation, when we do translation in the software, the rotation in the software of a 3D cube, and when we scale the cube, this is how it comes. So thank you. So this is Team Benjamin. Thank you once again.